So now, very important thing is, let's say for practically considering a frame, and I wanted to calculate for a particular story the lateral flexibility. Okay, so let's say this is some multi-story moment resisting frame, and it is subjected to this kind of cumulative shear force. And when it is subjected to, let's say, lateral force from wind or this, you can calculate at all the story levels the shear force, right? And when you look at it for a lateral load for a moment resisting frame, it's uh, we can assume these inflection points to occur at the mid location of the beams like this, right? And also at the mid height of the columns. Okay, so this is the thing. So if I take this typical story segment, and you will also find that, let's say I'm doing a 20 or 25 or 30 story building, and I'm looking at between 15th story and 16th story. If I take a free body diagram, okay, then between 15th story and 16th story, you will find that let's say the shear force is not going to change much, because the lateral force variation is also not going to change much. So we can say that the shear forces are approximately same. Okay, and again I'm saying that for lateral load, it's a good assumptions to find that the inflection points or hinges are going to form at mid span of each beam and at mid height of each column. Okay, and again I said, when you have a very tall building, uh, for an intermediate story, between the successive stories the shear force is not going to vary much, so we are going to assume that in a typical story the shear force is going to be constant. Okay, is an assumption that I'm making to derive an expression for lateral flexibility. Again, what is lateral flexibility? It is basically delta naught by shear. Okay, this is what we are trying to calculate again, right? So flexibility is inverse of stiffness, so that is why stiffness is vu by delta naught, and here we are talking delta naught by v. Now, how to calculate this? If I take this simple story and with an assumption that I'm having point of inflection at the mid height of the column and mid location of my beams, then what we can do is we can make two assumptions by uh, what will be the deflection when one column is only rotating and beams are going to be rigid, and what will happen to what will be the value of deflection when uh, columns are going to rotate as a rigid body and only because of the girder. Then I'm going to add them up to find what is the total delta naught. So my objective is to calculate the deflection delta naught, right? So first we will say that we are going to calculate deflections only coming from column rotations. Okay. So when the number of stories is large, again we have said that it is reasonable to assume that the shears in the columns above and below the floor do not differ appreciably. That means the shear force is not going to change dramatically. So for this case, if I take the free body diagram of between those point of inflections, and you will find that this is basically going to be your, see, the beams are all remaining straight. We are calculating delta 1 that is coming from only the story shear because of the column rotations. Okay, so that is what we are looking at, and this entire story is subjected to shear of V. Okay, so let us look at now what is the deflections. So now you'll find that if I take this small, um, if you find this as your thing, and you, this is basically going to be, now this total thing is delta naught. Okay, this to this is your delta 1, and this is going to be delta 1 by 2. Okay, so from here to here it is going to be delta 1 by, now lateral deflection delta 1 by 2 of each column is basically going to be the deflections. Delta 1 is basically delta 1 by 2 plus delta 1 by 2. So you can see that this really approaches the case of a fixed condition. You have a cantilever like this, okay, and this is again the cantilever like this. Basically, what we are looking at it is this. If I take a straight line, right, and this is what we are calculating. Now you can say that this column can be idealized as a cantilever with a height of length h by 2, and it is subjected to a story shear of V. Okay, so we know what is the deflection for a cantilever subjected to a point load, right? So we know how to calculate. Let's say this is your cantilever, and let's say this is your, let's say, V, right? So how is it going to deflect? It's going to deflect like this, and this is going to be your delta. So we know it is going to be V. Let's say the height is, if I'm taking that as h, the delta will be V h cube by 3 is basically 3I is going to be your delta. In this case, what we are considering is the height of the column is h by 2. Okay, so the shear that is acting is V. So if I plug in this, and the deflection is basically what we are calculating, delta 1 by 2. So delta 1 by 2 is going to be V into h by 2 cube divided by 3I. That works out to be VH cube by 12EI. Okay, so this is the deflection that is happening because of column rotations only. Now, your girder also will rotate. It's not that I'm saying girder will not rotate. I'm making an idealization to simplify the calculation so that, assuming that the entire system is going to remain elastic, principle of superposition is valid. So I calculate delta 1, and then I calculate what are the deflection that is coming from girder rotations. Then I add them up to get my total delta, right? So this is basically the way we are doing, because this is a simple free body diagram with a lot of assumptions of point of inflection is going to be at the mid height of the columns and mid height, mid length of your beams. And you must have studied in your structural analysis, portal method and cantilever method. These are all reasonably very good assumptions. So with which we have calculated now what is deflection due to column rotations. Now let us see what happens for all the columns. Now when you look at it, now again, this is for one column that we did. Now if I know the number of columns in the story, and then instead of IC, I have to sum the stiffness, okay? Because the elastic modulus of the column is not going to change, because usually for columns are all cast with the same grade of concrete for a particular story. So the elastic modulus is 5000 square root of FCK. When FCK remains constant, E is going to remain constant. There is not going to be change. So I can just multiply with the moment of inertia, the summation of your moment of inertia to get my delta. For when you have multiple columns, single column, this is the deflection. When you have multiple columns, IC has to be summation of your moment of inertia for all the columns. Now, next step. What is the deflection that is coming from girder rotation? So now you see here. Now, when the girder is rotating, it is going to take this column and see. Anyway, it's a rigid joint. So when the girder is rotating like this, right? So this is going to rotate this when this girder is rotating by theta, and the column is going to rigid. So this is also going to be theta because the rigid joint. So when the beam is rotating, it is going to shift the column also by the same theta magnitude. So if I fix this theta, then this delta is going to be basically theta times h. So delta is going to be, let's say this as delta 2, theta times h, where theta is your girder rotation, right? So the total internal moment for each girder is going to be 12 EI into theta by L. Now, how do we get this 12 EI into theta by L? So this we can take it from your fixed case. Let's say I take this fixed girder. So for a fixed case, we know that to produce unit rotation, how much moment that I need to apply? It is going to be 4 EI by L into theta, which is equal to 1. Okay, so I need to apply, if I need to rotate it by theta, I have to apply this moment of 4 E by L into theta. Now the theta, I am going to take it equal to 1. Right, so this is the moment that I need to apply when your far end is fixed. Now you see here, this is the thing. So because the far end is fixed, now you have to carry over that moment from your structural analysis. You may remember. So how much moment you are carrying over? In the same direction, it will be 2ei by L into theta, right? Now I'm doing the same thing for the other end. Okay, let's say this end I am fixing, right? Now other end I want to create in the opposite direction. Okay, so this is basically going to be okay. So now how much is the moment that I need to apply here? I have it to create theta equal to create a rotation of theta. Here I have to apply 4ei by L into theta. Now because this end is fixed, again I carry half of that 2a by L into theta. Now for this girder, because why we are doing this? This plus this. Because we want to create this deflection. What is the deflection? We want to create this deflection. Okay. So that is what. So when this plus this becomes this. So where you have theta here and you have theta here. Okay. So if you look at it, then for a particular girder to create a rotation of theta at left and right support, how much moment that I have added? 4a by L into theta plus 2a by L into theta at one end. Now what happens to the other end? Again 2a by L plus 4a by L. So for one particular girder, what is the total moment that I have applied? 6a by L into theta at one end, 6a by L into theta at the other end. Right? If you look at it, the addition, the total moment that I am applying to create this kind of a deformed configuration is 12ei by L into theta. Right? Now, when you have multiple such girders in a particular story, then what I have to do is then I by L, I have to add all of them because the length of now beam can be different. Column length will not be uh, different. That's what when you looked at deflection due to column rotations, column height is always kept the same because story height will always be same, right? But in beams, depending upon the span requirements, your length can be different. That is the reason in stiffness factors, I have to consider I by L for all the girders. So the total internal moment due to girder rotation is going to be 12e theta multiplied by IB by Li, where Li is your length of your each girder in a particular story. Now the external moment has to be equal to the internal moment. So external moment is, if we take moment about this point, you will find that V into H. Okay, this height is H. So V into H is your external moment. External moment has to be equal to internal moment. So when you add them up, you will find delta 2, which is theta H, should be equal to 12 EI into delta 2 into sigma summation of IB by Li, which is basically VH square. So theta is this. So when I multiply by H, should be equal to VH square. So I can find delta 2 in terms of V and the beam properties like this. So delta 2 can be expressed in terms of V and beam properties like this. Now what is our interest? I want to find the lateral deflections from column rotations plus girder rotations. So it is going to be delta 1 plus delta 2 is your total deflection for a particular story. So total story deflection due to column and girder rotations. Now I am adding this plus this. So this is your column rotation. This is your girder rotations. Now when you add them up and simplify them, if I take VH square by 12 outside, then you can get in this kind of expression. And again, lateral flexibility. Now what we want is flexibility is delta U by VU. So I take this VU this side. So and then I do some simplifications. Then you will find that delta U by VU will become HS square, which is the height of the story, multiplied by 12 times E of your column. And this is in inverse. Okay, this is in inverse. These are all of these things are inverse. So you will find that this is your lateral flexibility. So in this way, I can find out a simple expression for your uh, lateral flexibility. So the moment you are given the moment of inertia of columns, height of the columns, moment of inertia of beams and length of beams, you sum all of them in a particular story, you plug into this equation, then you can find an expression for your lateral flexibility. Okay, so the lateral flexibility can be found out for a particular dimensions that are for a structural members that are given to you. Now let's run through this example to calculate um, how we can calculate this slenderness ratios. Let's take this typical plan. I have beams that are running in the x direction as 300 by 600 mm cross section, in the y direction 300 mm by 450 mm cross sections. And this particular plan has 6 meter spans in the x directions, 3 spans, and 4 meter spans in the y directions. So the total width of the size of the building is 12 meter by 18 meter. Now let us see. My objective is to find effective length LEX and LEY. Okay. So how to do that? So let's say the typical story height is taken as 3.75 meter. Let's say I have done all the calculations. The axial load in the columns for a particular story is 7,500 kilograms. Summation of PU. So this is nothing but your summation of your PU, right? Is the axial load, and we are going to assume M40 grade for columns and M30 for beams. So let's see now what is that we're getting. If I'm taking this interior column, the column dimensions are all 300 by 300. I'm assuming. Let's say what we're getting. First, we have to calculate unsupported length of the column. Let's say what is unsupported length. Now, again, unsupported length when it is bending about. See, this column is also, again, I said, part of this frame. It is also part of this frame. So depending upon which frame, that direction that you are calculating, appropriate dimensions you have to calculate. So if you look at this, if I'm looking at this particular column in this direction, right, the C1 column that it is marked there, then you will find that this beam which is running along X will have 600 mm deep. The beam that is yellow color, which is running perpendicular or along the direction, then you will find that that is basically 450. Okay, but you will find that LX will be when it is bending about this x axis. So LX is basically how are we getting this LX. So basically, if you look at this particular frame, this is your x direction and this is your y direction. So your total height is going to become 3000, let's say 750 is basically the story height. That means the height from the top floor to that other top surface of the other floor is 3750 millimeter. 3.75 meter is the story height. Now what is your unsupported length for bending about x direction is basically 3750 minus this 450, okay, which is the bending about this axis. Okay, so Lx will become 3300 and Ly will become 3750 minus 600, which is basically your unsupported length for the column when you're taking bending about y direction. Okay, so this is how we get your for buckling about y axis, and for buckling about x axis it is going to be 3300, right? So if you go back, and our objective is to calculate stability index first to determine whether this column is part of the braced frame or unbraced frame. To do that, I need to calculate again lateral flexibility, that what we derived now, which is delta naught by Vu, summation of Pu that is already given to you, 7500, and height of the story is given to you. So let's plug in. The important thing is to calculate the lateral flexibility equation, which is this. So for this particular case, that what we have considered, if you see how many beams, let's say if I'm taking this particular case, I have 3 beams, right? And similarly, how many columns? 1, 2, 3, 4 columns. Similarly, in each directions, I have 4 columns and 3 beams. So let's look at now. Okay. So the summation of your, okay, sorry. This is, we are doing it for the entire story. So you'll have 16 columns. Okay. So if you go back, in each directions, you have 16 columns, right? when it is bending over. So square columns. So the moment of inertia BH cube by 12, 300 into 300 cube by 12, and height of the story is 3750. So when you do the summation, you get this summation of IC by HS like this. Similarly, you go ahead and do for beams. Okay. For sway, which is happening in the X direction, which beam is going to happen? It is a longer beam, okay, or a deeper beam, and also the length is of each beam is 6 meter or 6000 millimeter. So the moment of inertia of this cross section is 300 into 600 cube by 12, and these are basically 12 such beams are there. So let's go and calculate this. Okay. So you see here how many beams are there in the shorter direction? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So 12 such girders. Similarly, if you look at it on the y direction also, you'll have same number of girders. But only the moment of inertia of the beam that we need to consider has to be different. So if you see that we have 12 such beams, when you multiply that, you get the total stiffness of all the girders is 10,800 into 10 to the power of 3 millimeter cube. So now for the sway in the global y direction, again, the moment of inertia is going to be 300 into 450 cube by 12. All of them are having same dimensions. If you're having different beams for different spans, then again, appropriately, I have to add them. In this case, we have taken all the beams to have same dimensions, both in the x and y direction. That is why there is no change. Otherwise, I have to, for each beam, I have to calculate that IB by LS. So in this case, it works out to be 6,834 into 10 to the power of 3 millimeter cube. So once you got all the values, so we plug in this, and E value again is coming from 5,000 square root of FCK. For all the columns, it is going to have the same elastic modulus of 31,622. And for beams, because you have 30 megapascal strength, elastic modulus of the beam is going to be 5,000 square root of FCK, which is 27,386. So you plug in this, and you have already calculated. This is inverse, okay? So when you do that and plug in these values, you find that the lateral flexibility is in the x direction is 1.683 into 10 to the power of minus 5. Similarly, we do it for y direction, and you find that why is that in the y direction you have more flexibility? Column dimensions are same, square column 300 to 300. So why is the case that you have higher flexibility in the y direction? Because beams which are running in the y direction is having 300 by 450 mm, but in the x direction you have 300 by 600. So the moment of inertia of beams that are part of this y direction frame are going to be less. So it is going to be more flexible in the transverse direction. So that is why you get a higher value. Now that we got these things, so I can calculate stability index about both the directions. So in the first x direction, PU is 7,500, it remains same. Height of the story is 3,750, and lateral flexibility is this, and you find that it is 0.034. Similarly, for y directions, flexibility is higher. Though it is higher, I get a flexibility stability index of 0.038. Both of them are less than 0.05. So that means, though I do not have shear walls in this particular case, the dimensions of the columns and beams are quite adequate, right? So the columns in the story can be considered as braced. Now, why is this important? Then only I can go ahead and use the alignment charts or equations, appropriate chart and appropriate equation. First, to use a chart, I need to know whether the column is part of the brace frame or unbraced frame. So to do that, we calculate the stability index. So once we have done that, then you get your effective lengths by I-square charts, and you calculate, or you can use this equation also. And now we get your beta 1 and beta 2 values. Again, now how to calculate beta 1 and beta 2 at top? In summation of IC by HS of members that are connecting at the top joint. Now we have same system at the top and bottom. So again, so beta 1, beta will be same values. So you find that IC by HS is this, and IB by LB is this. So if I substitute that, I get beta 1 and beta 2, same value of 0.286. So now that I got beta 1 and beta 2, I can go ahead and find out where this point is. So for example here, 0.286, sorry, 0.286 that we go, and 0.286 we go. So you get a value of roughly between zero point 0.6 and 0.575. So K value is going to be between 0.575 and zero point 0.6. Of course, we can do the interpolation and you find K value equal to 0.588. So my effective length is going to be 1858 millimeter only. So it is going to be definitely a short column. Okay, because the K value, you see, again for a braced condition, K value is going to be between what are the zero point 0.5 and 1. So maximum value of K is going to be 1. So this is K value is coming very close to that of zero point 0.5 means what? Basically these joints are very rigid and it is approaching a fixed condition. It's not exactly fixed, but it is approaching. If this zero point 0.5 value becomes close to that of zero point 0.9 or 0.95, then we can say that at both ends they are approaching a pin condition, right? So using this, again, we can find out the effective length. We can, right? So now what we can do, again, effective lengths by IS code charts. We have done this. So about now we are doing that about other axis, right? So again, this value is 360, this value is this. So if you substitute that, then you get value of, again, why are we using this zero point 0.5? Because it's a braced frame. From stability index, we found that it is a braced frame. For the other direction, your K value works out to be 0.625. So because it is a little bit more flexible, so it is the K value is slightly increased. So then in this case, that's why it's for same column. Now in X and Y direction, you can have different effective lengths. But in this case, is because it is part of the brace frame, the effective lengths are not increasing. But if it is an unbraced frame, the effective length is going to be very high. So in this case, if you substitute LE by dy, which is in this case it's a square column, so dx and dy is same. So if you substitute that, you get a value of 6 and 6.87, and again both of them are less than 12. So as per code, when it is less than 12, it has to be designed as short column. This column is a very short column. You don't have any slenderness. Again, for the same column, if you go back, same system, instead of having height of the story as 3.75, if I'm having a height as let's say 6 meter or 7 meter, you will find that uh, the Q value will become more than 0.05, and you will end up having the same frame will become unbraced or a sway frame. So it all depends upon what is the height of the story, what are the dimensions of the member that we considered. Okay. In this case, for the proportion that we have considered on a height of story of 3.75 meter, the Q value are less than 0.05. So we call this frame as a braced frame. But it all depends upon the sizes of the members that are connecting the joint, and also the more importantly the height of the story. If the height of the story is very large, if you have a double story height or 3-story height for a column, then the column will become slender column. All right. So let's wrap up what we have discussed in this part of the module. We have discussed the classifications of columns based on the shape, the length, load, and we also discussed the behavior of slender column. Why is it important? Because of the additional deformation that is happening, that is going to create additional moments. So that we have to account for them in our designs, which we will discuss. And we discuss more importantly the effective length. The effective length is what is going to tell you whether that will be used to calculate your slenderness ratios. That will tell us whether the column is a short column or slender column. And then we also talked about the difference between sway and non-sway frames. We distinguish the frame as a sway or non-sway by calculating stability index. For calculating stability index, again we have to use the lateral flexibility. That again we derived what is the expression for a lateral flexibility, and we also calculated stability index and effective length by using an example. Right. So I would again like to thank my MTech student, Mr. Ranjit Kumar, for helping me with the preparation of the slides. And thank you. So we'll continue in the other parts of the module. Thank you.